All right, so 15.4 in your textbook, Snell's law, a general equation. So this is, we're still talking about Snell's law, but it's adjusted a little bit, and I'll tell you why we have a general equation and why it's different from the one we just talked about. If you recall, we just talked about this one right here, and this is called Snell's law, but you have to remember that this right here only happens when the incident ray is in air and the refracted ray is in another medium. And so if the incident ray is not in air, then we have to adjust that equation a bit. And so what happens if a light ray comes out of water, into diamond? Well, then this light ray coming out of water is going to behave differently going into diamond than the light ray coming out of air would have. So let's say this is the light ray that would have come out of the air, right? Or vice versa. Actually, I think it would be on the other side of the line. But anyways, it's going to be different if it's coming out of the air. So it actually would be over here. Maybe we'll explain why that is a little bit later. But it's going to be over here. It's going to bend more going into diamond. But if it's coming out of water, it's already slowed down a little bit. You see that? So it doesn't have to slam on the brakes so much. So there's going to be different rules governing how the refracted ray is changed. So the original Snell's law only dealt with the index of refraction of the material the light was traveling into. What if the light were not traveling from air, but from something else? So that's basically what we're saying here. Okay, so I'll just highlight this. If light were not traveling from air into another material, then we need a different equation. So, for example, water into diamond. So what you need to copy from here is basically that we need to adjust Snell's equation if the ray is not coming out of air, not coming from air. So in this case, we would need to take into account the difference between the index of refraction of the material that the light had been in and compare it with the index of the material it's traveling into. So like I said, the light ray is going to behave a little bit differently coming out of water into diamond as opposed to coming out of air into diamond, because the light rays have already slowed down a bit. And so we have to change the formula. So this is Snell's law in general form. So Snell's law in general form. And let's take a look at it. It's not that tough, actually, at all. Okay? But it looks like this. N1 times sine of theta 1. So that's the index of refraction of the first material and the angle of incidence in that material. So that's why we have the 1's here and here. Okay, so that's in material 1. Then we have the n, or the index of refraction for material 2, and this is the angle in material 2. So this really would be the angle of refraction. So this right here would be I, and this right here would be R, angle of refraction. So you see that down here as well. Theta 1 is the angle of incidence, because it's where the ray is coming from. Angle 2, angle of refraction. All right, so I want to just show you something here. This is very, very similar to the first one, to the first equation, but let's say that the incident ray was in air. Okay, the incident ray was in air. With this equation, this n right here is going to be 1, or technically 1.003, right? And then you're going to have sine of your angle of incidence. Then you're going to have over here whatever your n2 is, and you're going to have the sine of the angle of refraction. So in a vacuum, or in air, which basically the speed of light is virtually the same, this is basically times 1, right? Times 1.0003 is basically times 1. So if it's in air, this is 1. And so what do we have? We have sine I equals n times sine r, or n equals sine I divided by sine r. So you see how this is the first equation? That's the original equation right there. But now we're taking into account the fact that this n, if it's not in air, this n is not going to be 1. So we have to account for that. Okay? Alright, so let's take a look at some examples here and how you would use this. And it's pretty basic. It's pretty basic math. But let's do some examples here. So Snell's general law. Okay, we'll do some practice here. All right. So for this example, this says light travels from crown glass into air. The angle of refraction is 60 degrees. What was the angle of incidence of the glass? So here we have air. Okay. So we're traveling from the glass into air. So I just want to pause. I'm going to do a little sketch here first. But when we're coming from a slower medium, light traveling in a medium when it's slower, and then transferring into a medium where it goes faster, does the light ray, okay, so let's say this is the incident ray here, okay, is the light ray going to bend towards the normal, or is it going to bend away from the normal? This is a question you should be able to answer without doing any calculations. You should be able to know this. So if it's going to go faster, does it bend away from the normal, or does it bend towards the normal? Okay, from your work already, hopefully you've seen that it's bending away. And from the pages before in the past when we looked at that, all the diagrams going from air into something where it slows down bends towards the normal. So yes, you're right. This is, oops, let's go forward there. Yeah, so it's coming into air and it is going to bend away. So if the angle of refraction is 60, the angle of incidence should be what? Greater or less than 60? Yeah, it should be less than 60. So that's what we're looking for here. And it's a good idea when you're doing these questions to try and think through what you should get first, knowing what you know. All right, so let's write down that equation. N1 equals, N1 times sine 1, sine theta 1, equals N2 times sine theta 2. And I've talked to you guys about theta, right? Do you know when I say theta what I'm talking about? This is a Greek letter, and it just represents an angle in math and science. All right? So we could put I and R there too. That's fine. Okay? So in glass, what is the index of refraction? What's the index of refraction in glass? Let's see. Crown glass. So we've got different glasses there. Where's crown glass? 1.52. See that? 1.52. And the angle of incidence in the glass, well, we don't know. So we're going to do sine theta 1. Okay, that's the unknown, so we'll just leave it there. In air, okay, the n in air is 1.003, and we have sine of 60 as the angle of refraction, angle 2. Okay? Alright, so in most of your calculations, this isn't really going to make much difference, this 3 in here, but let's do it anyways. Okay? So how do we get theta all by itself? Well, the first step is dividing both sides by 1.52, and we get sine theta 1 equals this over here, and we may as well do this on our calculator. Let's just clear this. So, and just to make sure you don't make any mistakes, you might want to just do the top and then hit equals like I do here. Make sure you're calculator's in degrees, not radians or something else, and then do the division. So this is what I often do so I don't make operation errors there. Just do it in pieces. Okay, so we get 0.57146, 0.57146. Now you should leave, use the entire decimal, of course, on your calculator, so don't clear this off. Leave this number in here when you do your next calculation. Okay, so how do we find theta? How do I get rid of the sign here? Yeah, don't divide by, you can't divide by sign, okay? This doesn't make any sense. Sign is no good on its own, okay? That doesn't make any sense. So you can't do that. Instead, what you have to do is you have to, do sine to the -1, really. So that's inverse sine on your calculator there. And that basically gets theta by itself. That's how that works. So theta 1 equals, and you can just use that number right here. So I'm going to do second function sine, and then I'm going to plug in the answer, and you should have some kind of answer button on your calculator. And then you should end up with that right there. So 34.85 or 34.9. Alright, yes, this should be 1.003. Thanks for noting that. So let's do this again real quick. 1.0003, didn't hit my final 0 there, times sine of 60. It's going to give us a slightly different answer down here. Might not make a difference, but we'll see. Divided by 1.52 is that number there. Yeah, so we got a little bit of a difference there. And then second function sine of the answer. There we go. So 34.7 instead of, so 34.74. 0.7. Now, a lot of times they'll ask you to round the degree to the nearest either tenth or the nearest degree. So you just have to watch that. But so it's less than 60. That's right. And we've got 34.7 degrees is for the angle of incidence. Okay, pretty easy. Yeah, just make sure you get all your zeros there when you're doing your calculations. Okay, so you guys should be good enough in math at this point where you can solve for any one of these, right? You can solve for your theta or your n's. So that shouldn't be a real big deal here for you, okay? But that's Snell's general equation along with an example. All right, 15.5, page 470. Excuse me. We just talked about Snell's general equation, and we're going to talk now about this total internal reflection and the critical angle. Okay? So there's a couple things we need to talk about in this little section here. All right. When you're traveling from a fast material, so the speed of light travels very quickly, so something like air, to a slower material, the angle of refraction is less than the angle of incidence. Okay? We just finished talking about that. But the opposite is true when you go from a slow medium to a fast one. And we also, in our previous example here, that's sort of what happened, where it was our work right here. See that? Slow medium to a fast one, the opposite is true. So if this angle was coming out of air, it would slow down and go towards the normal. But if it's coming out of glass, let's say, it speeds away from the normal. The angle of refraction is greater than that of the angle of incidence. Okay. So we just finished talking about that in our last page there. So this is what this is going to mean, and I'll make this just a little bit bigger here for you. Yeah, I got some cool pictures there. This is what this means, is that it's possible, okay, for light to be refracted so much that it never actually leaves the medium. So you want to copy this entire sentence down, okay? It is possible for light to be refracted so much that it never leaves the medium. When this happens, it's called total internal reflection. Where you may have seen this is something like, in a swimming pool, if you're swimming in a lake and it's fairly clear. If you swim down deep and then you look up at the surface, you can, there's part of the, you can see out of the water a little bit, but you can also see the reflection of the bottom of the pool. Okay, or you can, you can see the reflection of other people swimming. Um, so there's a certain angle. So let's say this is you right here. Let's say this is you. You can look up and you can see things that are above the water, like the clouds or people up there or whatever, the diving board or whatever. But if you look at a great enough angle, you'll see the reflection of the bottom of the pool over here. That's what you'll actually see over here. You'll see people and stuff, and then you'll see, boom, you'll see the bottom of the pool, or you'll see people's, feet. That's a really warped foot. But here's another foot, okay? You see that? You see someone standing over here. You see that? Okay, here they are. Something like that. Okay, so what's happening is that this light ray, you see these light rays, how they are being refracted, they're being bent away from the normal? Well, there comes a point where the light ray would be refracted right along the border of the medium. And then anything beyond that, that light is not going to escape, and instead it's going to bounce off and reflect. Okay? Okay. The angle of incidence that has a 90-degree angle of refraction and therefore sends the light skimming along the surface, as I just mentioned right here, is called the critical angle. So because all of this happens, there is a certain angle at which an incident ray will just barely, skim along the surface. It's sort of the angle that cuts off between actually the light rays coming through and the light rays getting reflected. This is called the critical angle. So again, it's the angle of incidence that has a 90-degree angle of refraction. It's called the critical angle. And if we skip down to this little diagram here, all right, so this person, this camera, is taking a picture of the fish, but also they are at such an angle that these light rays, okay, that the fish that's bouncing off the fish, all right, they are bouncing off the surface and coming to the camera. So that's why you see kind of a double image there. Now, if this camera were turned and it was looking straight above, you could see, what's above the pool. But at an angle, the light rays just bounce off within the medium. So any angle of incidence that's greater than this critical angle will result in total internal reflection. Okay, important sentences. Make sure you've got those written down there. All right, let's look at some examples of substances that use this idea of total internal reflection. Okay, so I don't know if you guys recognize this right here. This is, anybody know? It's fiber optic cable. Okay, and basically, yeah, it's kind of like, it's basically, flexible, sort of glassy substance, and basically there's light signals that get passed along this, and it's super fast. If you guys have your internet connection, if it's the new fiber optic cable, it's quite a bit faster than the older style cable, because the light signal that comes in, okay, for your internet or cable TV or whatever it is, it actually comes in and it keeps bouncing off the inside of the glass. So it doesn't get shot right through, but whenever it hits the side or the inside, see, this light ray is not going to escape, because this is glass and this is air. And what happens is when it gets shot down here, the tube, it just keeps bouncing off. And if you think about it, some light will escape, I suppose, if you have a light ray that happens to bounce, like this, and it bounces up, and oh, that one might escape. But most of the light rays are at an angle that they will keep on reflecting. See how it races down the optic cable there? So here's an example too of a plastic tube and a laser beam, where you kind of see it doesn't escape. You see it bounces off inside, and you see it kind of keeps going like that. The same sort of idea. So total internal reflection is quite useful in industry and our everyday life as well. Okay? Any questions about that? All right. Before we move on, let's just talk about the critical angle calculation. Okay, how do you know what the critical angle is for a specific medium? Okay, for glass or for plastic or something like that. Well, remember what we said about the critical angle. It's the angle at which light now does not escape. So if we have, an angle like this, an incident angle, and it's bending away from the normal, there will be some angle right here where the refracted ray is exactly 90 degrees. And so we can use Snell's general equation and find out critical angles for certain things. So let's figure out what glass is. Okay? So this is how we do it. We look at our chart and we see that the N for, let's use crown glass, we used before, is 1.52. That's the index of refraction. Okay? So let's say this is the glass here. Okay, and we're going to go into air, right? And we're going to find the critical angle. So this right here is the critical angle. See. So Snell's law says, N1 sine theta 1 equals N2 sine theta 2. Okay? So let's take a look at what we need here. Well, the N1 is 1.52. Okay, so let's put 1.52 here. This critical angle is really the angle of incidence, right, in this situation. So we don't know the angle of incidence, theta 1, so we'll leave this sine theta 1. The N2 for air, we're going to say is just 1, and we're going to use 1 from now on because I think the textbook does, and like I say, for our sig figs, we don't, the 0003 doesn't really matter. So in air, we're going to treat that index as 1. And what's the angle of refraction that we're looking for? 90. Yeah, sine of 90. All right. Now, does anyone know what the sine of 90 is? Is it? Okay, let's just check. Sine of 90, talking about degrees, very good. It's 1. So look at what we actually have here. We have 1.52 times the sine of theta 1 equals 1 times 1. So the sine of theta 1 equals 1 divided by 1.52. Because 1 times 1. So here's where the n goes, and this would be the critical angle. So really, you could, if you wanted to, this isn't in your textbook, but the sine of C, critical angle, is 1 over n for that medium. Okay? That's how, if you want to, this is how you find critical angle. Okay, so critical angle here is sine to the negative 1 of 1 over n. That's how you find the critical angle. So let's continue on with that. Sine to the negative 1. So we have theta 1 equals so the critical angle for crown glass is 41 degrees. Okay, that's the critical angle. It's 41.1 degrees. Which means that, okay, if this is 90 here, anything, so this is 45, so 40 degrees would be right about here. Any angle of incidence greater than this is going to be totally internally reflected. So right now we have this here, and it's reflecting right along the surface. So any of these angles, if it's greater than 41.1, is going to get reflected. That make sense? All right. So I tell you what I want you to do is I want you to find the critical angle for diamond right now. So go ahead and just spend a minute doing that. Find critical angle. Yeah, I know it's in your textbook. Yeah, use the calculation. You might find it in your textbook, but show the calculation just to confirm. Okay. So I know you guys probably done it already real quick. Use our new formula here. The critical angle, if we let it equal to c, and then that's the sine of negative to the negative 1 of 1 over, what's the index, 2.42. Okay. So the critical angle is second function sine 1 divided by 2.42 equals 24.4 degrees. 4.4 degrees. Okay, so we are going to talk about more about diamond and stuff, because diamonds are kind of a cool thing, and that's because light slows down so much and it has such a small critical angle. So if we're talking about an angle of 24 degrees, I mean, that's pretty small. Here's 45, right? And half of 45 is 22.5, so it's pretty much half of 45. Pretty small for a critical angle. So this opens up the door to most light rays, right? That would come in here. And inside a diamond, that's why you have a lot of total internal reflection. Very few of the light rays actually escape out of the diamond. So that's why it's so sparkly too, right? You can see light bouncing around inside there, and it naturally kind of diffracts the light a bit, and you get the colors and stuff. That's why it's so sparkly, because there's a lot of light being trapped inside there. It just basically keeps spinning around inside that diamond. It keeps bouncing around and then it escapes every once in a while. And so it's, yeah, pretty cool. So we'll talk a little bit more about that. But I do have a video queued up here for you that I just want to show you. And this video here is about critical angle and total internal reflection. So if somebody wants to grab the lights there, that'd be great. Okay, let's just see what they have to say here. So just got a pan of water and a laser.
Now, light rays start because I'm going to use low index of air to high index of water.
Okay, let's just stop this for a second. You see, here's the angle that the laser beam is coming in at, and here's the angle that it's going into the water at. Now, these are, I mean, this is displaced a little bit because of, we're seeing this laser beam through air and we're seeing this one through water. So remember, there's different things at play here. But what you want to notice is this angle and this angle.
So there's no critical angle.
When you're going from air into water, there is no critical angle because it always bends towards.
High index of water to low index back to the surface. First up, I'm finished shooting the light straight to the water. As you can see this way, there's no reflection. As I start go upward, now
You see?
there's a reflection.
So this angle right here is greater than the critical angle, right? So, and notice that it's not escaping out the top. See, there's nothing up there.
Light is able to penetrate from the outside. As you can see, my finger.
So some light is escaping through the side, I guess. I'm not sure. It's filming just right there. Back to the water.
The light is no longer here. That means critical angle. I exit I get what is called total internal reflection.
Okay. All right. Now I'm just going to pause it there. Okay. Now, what I would like to have seen, and maybe we can, maybe we'll see this at another time. But if the angle is coming up from the bottom, right, at a sharp angle, that light will come out, and as that angle increases, it'll still come out, and then it'll just be reflected. Right. So this is basically total internal reflection, and you see that no light is escaping there. Okay. Any questions? Okay, what's the critical angle for water? Let's calculate it. What's the critical angle for water? The critical angle for water is going to be sine to the negative 1 over, what's that? 1.33. So second function sine, 1 divided by 1.33. 48.7 or 48.8, you guys get that? 48.8 degrees. So any light ray that has an angle of incidence in water going out to air that's greater than this angle of incidence right here is going to be totally internally reflected. All right, so I'm going to set you back. Let's see, where were those questions? Okay, so you can do these questions here. I think we've done some of these already, right? So the 470 is going to be new, and also 472 is the critical angle question. So you can add to this page 472, numbers 1 to 3.